Hi everyone, and welcome to the third of 4 videos going through some past exam questions on the topic of intermolecular forces. This question here we've got about halogens again, which is somewhat similar to one of the questions we've seen in one of the previous videos, but it's slightly different in a few places. First bit is this one. It says solid chlorine and solid bromine have a similar structure. What is this structure? We need to name it. It's what we would call a simple molecular lattice. Okay, and it's a bit of a strange term, this, because it sounds like a contradiction that you're saying a simple. How can it be simple and still be a lattice structure? It's because it's a lattice made up of simple molecules that are bonded together. Now, normally, it's only intermolecular forces that are holding these simple molecules together, and they're a really weak force. Okay, but the only reason you'd end up with solid chlorine or solid bromine is at a very low temperature, where there's not enough energy to overcome the intermolecular forces, and so those intermolecular forces hold the simple molecules in a lattice structure. So that's just a 1 mark question that we need to know. It then says the intermolecular attractions are van der Waals forces. We mentioned this before. They won't use the term van der Waals forces, they will use the term London forces on the new specification. So we then need to explain how do London forces arise between halogen molecules. So this is very similar to a question that we've seen before. The first thing we want to talk about is the fact that the electrons in the molecules are constantly moving and become unevenly distributed. So just by chance, we end up with more electrons at one end of the molecule than the other. Okay, this creates a temporary dipole, where because we've got more electrons down one end of the molecule, that end of the molecule ends up slightly negatively charged. Okay, and the end of the molecule with fewer electrons end up slightly positively charged. The temporary dipole that we've got then induces a dipole in the neighboring molecule. Because then in the neighboring molecule, the negatively charged end of one of those molecules then will attract to the positively charged end of the neighboring molecule. So it's a fairly standard question. You want to talk uneven distribution in terms of getting your marks here. The uneven distribution of electrons, the temporary dipole, and then the induced dipole. That's where you get your 3 marks from. So then it's then asking us to compare the halogens here and compare the boiling points. So we can see that bromine has a higher boiling point than chlorine. Why is this? So this must be because the London forces, okay, we've already talked about the fact that it's London forces. So the London forces in bromine must be stronger than those in chlorine. And they require more energy to overcome. So there's always, we mentioned this point, taking more energy to break the forces is usually worth a mark. But why then? Why are the London forces in bromine stronger? It's because bromine has more electrons. Okay, if we go back to what we said here, the London forces come from the uneven distribution of the electrons. Okay, so the more electrons you have, the more unevenly distributed they can be. Okay, so this is because bromine has more electrons than chlorine. Okay, so that was all mostly about London forces. Okay, these questions here are slightly different. Here we're looking at group 6 hydrides, and we're looking at their boiling points. So we've got water H2O, H2S, H2Se, H2Te. Explain with the aid of a diagram the intermolecular forces in H2O that lead to the relatively high boiling point. So we can see its boiling point is higher there seems to be a pattern going on here, then this is definitely a bit of an anomaly. So why is H2O's boiling point so much higher? Well, it's because it's got hydrogen bonds. Okay, so that's what we want to draw here. We saw this in a previous question. So some of these questions that we're looking at here are very similar to questions that we've seen before, but I wanted to make that point of, look, the same types of questions come up, so make sure you can do them, because if you're prepared, you know what to expect, and you can be like, oh, I've seen this sort of question before, I know exactly what to do. So we want to draw two water molecules. We want to show the lone pairs on the oxygen atoms, and we want to show the dipoles. So the oxygen is more electronegative than the hydrogen. And then we want to show the fact that the positive, slightly positive hydrogen will be attracted to the lone pair of the oxygen. So this is our hydrogen bond. And we talked in the other video about making sure that it does attract to the lone pair. So we can say here that H2O has hydrogen bonds which are the strongest type of intermolecular force, and require more energy to overcome. And then, why does H2S have a much lower boiling point than H2O? Well, we kind of answered it there already, okay? So we can say that the hydrogen bonds in H2O are stronger than sulfur is not particularly electronegative. In terms of, we look at this going, does it have London forces or does it have permanent dipoles? Well, let's just look at what the data is telling us. If it had permanent dipoles, they're stronger than London forces. We'd expect its boiling point to be up here somewhere. The fact that its boiling point is lower than both of these two suggests that actually it doesn't have permanent dipoles. It's probably just London forces. Okay. We might not actually need to go that far. We might be able to get a mark just for saying the intermolecular forces. In fact, yeah, it actually doesn't matter. So I'm going to go for London forces. But we would get a mark if we'd just said intermolecular forces. And then, as we said, it's always good practice to say, and therefore require more energy to break. It's only a 1 mark question, so we probably don't need to, but I think it's good to get into that habit of always putting it in, because sometimes it might get us an extra mark. So it's always worth putting that